In this problem, we are going to look at a simply supported beam that has an applied force at one location and a concentrated moment or coupled moment at another location along the beam. And the dimensions are given as follows. There's a bunch of detailed numerical values too for the values. And we have a condition where we're saying that the applied moment divided by L is greater than the applied force divided by 4. And that extra piece of information may not seem significant at this point, but as we go through the problem, you'll see why I included that condition. So the question that we want to determine or answer is, what is the maximum bending moment along this beam? And we're going to use the integral differential equations to solve this problem, but the first step is still to perform external equilibrium. So whether using equilibrium in the internal slices and the internal analysis, um, or you're using the integral differential equations, we start with external equilibrium. So we have a force from this left end of the beam, and we have a force from the right end of the beam as well. And we already have these externally applied loads shown. We'll start off by looking at the forces in the vertical direction and setting them equal to 0. And when we do that, we have RL, we have FAP, we have RR. Of course, MAP is not contributing force. And when we look at summing the forces and setting them equal to 0, we'll do that at the left end. And when we perform this calculation, we'll see that we have a minus value from the FAP L over 4. Okay, that's going into the board, and essentially we're saying positive is coming out of the board. Then we have MAP, and we have RRL. So we can solve for the right reaction force here that we see, and we have the following for RR, and then we can go back to this equilibrium equation up here, and we have RL. So we discussed this in the class session. What is this? We discussed that these types of problems are determinate in nature, and we see that here, that we're able to use equilibrium to figure out what the unknown values in the problem might be. So the two unknowns were RL and RR, and we have now, through two equations, been able to solve and find values for them. Just a note, a minute ago, right, we said that if we go back here, that MAP over L was going to be greater than FAP over 4. Okay, so what that means is that this particular value for RR, right, MAP over L is going to be greater than FAP over 4. That means that this value is going to end up being negative, right? So this is actually pulling down. Yes, it is a roller, and so maybe we're suspending reality just slightly, but this force would be negative in value. And we can see that that can be possible, right, when you have this coupled moment going into the, or coming out, sorry, of the board. And that's kind of causing this to rise a little bit. And so there's got to be a downward reaction force here when this condition, when MAP over L is greater than FAP over 4, when the condition previously described makes RR less than 0. And you can kind of see that this FAP, right, that's kind of, it's applying a moment actually, and also a force to try to keep it down. So there would have to be a reaction force in the vertical upward direction on the right side. Values at the left side. So what does that mean? That means that we're going to look at slices or a slice just to the right, okay, of RL. And we'll do this at the right side as well. Okay, so in this case, we can figure out what the boundary conditions are going to be. We see that RL and V will be equal to each other, and we also see that there's no moment being applied externally to the system, so M will be equal to 0. So V of 0 is equal to RL, and moment at 0 is also equal to 0. The values at the right side we'll take a look here, and I guess it's also worth pointing out again that while we were able to select what we wanted for RL and RR, and maybe you're thinking, well, now that we know that this M app over L is greater than F app over 4, and maybe we should have selected an RR downward. Yeah, that would have been fine. That would have been a fine choice. But when it comes to these blue internal shear force and bending moment uh, uh, depictions, they have to be this way, okay, following the convention we're using in the course. Same thing here on this side. Once again, there is no moment being applied on the right side, and so the moment's going to be equal to 0, but we see that V and RR are going in the same direction, so V has to be equal to minus RR. So we see V of L is equal to minus RR, and that the moment at L is equal to 0. We're using the differential integral relationships, and let's go ahead and integrate. We see that the shear force is equal to the integral of w dx. This is just a constitutive, well, this is actually an equilibrium-based equation, and so not a constitutive-based relationship, but we find out here that, well, we don't even have to find out. We see that there's no distributed force applied here. So what does that mean? That means that W is equal to 0, and C1 is going to be the resultant here, right? So we have some type of constant. At x equals L over 4, we also have this delta V that we're going to be imposing on the system. So we have a minus F app. Okay. So let's go ahead and let's just copy this information over to a new page. What is this information? We're going to keep in mind these equations right here for RR and RL. We'll keep in mind the boundary conditions at the left side and at the right side, and we'll keep in mind that we're forming this integration. So, boom, right? RR, RL, these are the boundary conditions, and this is where we were with our integration and our understanding of what's going to be happening to the change in the internal shear force. It's going to be negative FF, and that's why if we're going from left to right. If we're going from right to left, then it would be the opposite sign. But this is this type of equation for the concentrated applied force, and the other one, the corresponding one for the concentrated applied moment, their signs are dependent on going from left to right. So let's do a little bit of graphing here. So we see that there's got to be some constant value for the shear force based on this integral equation. And then at x equals L over 4, there's going to be a jump. Well, if it's got to be constant, we know what it is on the left side. It's just RL. So that value is going to be RL. And then when we get to L over 4, that we'll call here, that value is going to jump down by a amount of minus FF. Okay? And the other thing that's interesting, right, is that is still this integral reveals that the shear force has to be constant. So it's constant and it stays constant, even though my line's a little bit slopey. But at the right side, we see that that boundary condition, so it has to be equal to minus RR. So that's the value it's going to end at. And since we've integrated this distributed force, which is 0 with respect to x, then it has to be constant there as well. So this might be kind of a simple idea, but it's subtle if you haven't done this type of problem prior. And once again, we have this jump, this delta V is equal to minus FF. And does that make sense? Well, yeah, it does. Look, if you see here, okay, that we have minus, so what's the difference between minus RR and RL? Well, we flip a sign, right? And or we yeah, you know, we can say Okay, put a minus RR here, right? So that would be, this is minus F app over 4, and then we have plus M app over L. And if we were to RL minus this negative RR, okay, so that's going to be the difference between them, right? What we're going to see, we're going to see that it comes out to be just minus F app, okay? So that's an interesting, well, maybe it's a slightly interesting observation. So we see that jump, okay, from there. And now let's look at what's happening with the integration of the shear force. Okay, so we're going to integrate the shear force. This comes from, of course, dv dx is equal to m. And we're going to go from 0 to L over 4. Okay, so that's kind of going, or we're thinking about that, okay? And we have a constant, so that means that we're going to have first order. And the slope is RL, so it's going to be RLx plus C2. And from this boundary condition, m of 0 is equal to 0, we see that, that this is going to be 0, or the C2 is going to be 0. And we're just left with this slope times x. So that can be graphed as we see here. Okay, so it's going to start at 0, the moment that is, and when or until it gets to L over 4, it's just RL times X. So at L over 4, it's RL times L over 4. Okay, so that's the value we see there. Now, going from L over 4 to 3L over 4, okay, so that's going from here to about that location. We see that the slope is then minus RR, okay? And so we ask ourselves, well, what you know what is that slope, positive or negative? Well, if we come back to the condition that we described, we have M app over 4 is greater than F app over 4. So RR, okay, if you have M app greater than of L greater than this F app over 4, that means that RR would be a negative value, but it's minus that. So that means that it's going to be positive. Okay, so the slope from here to here, it also has to be positive. Okay, or sorry, from there to about 3L over 4. What happens from 3L over 4 to L? Well, that slope also is minus RR. So that also has to be positive. So all the slope is going to be positive. All right. But there is a jump at 3L over 4 in the moment. Okay, it's going to say delta M has to be equal to minus M app. Why? Because this one's actually coming out of the board, which is positive, but the way that we derived this this jump in moment was for a coupled moment that was applied going into the board. So when we get to 3L over 4, we're going to have a minus M app. So what does this look like? Well, let's say this is 3L over 4, this dotted line. We'll just say that there's a delta M equals minus M app. We know we have a slope of minus RR from here to here, and we can also say that while it's positive, it's less than RL was. So that slope is going to be less steep. We get to this point, and then boom, it jumps down by some delta M. Now, whether it goes, how far down it goes is not quite certain, but guess what? It ends at 0, and it has to have a positive slope from 3L over 4 to L, which means that it has to go below 0 in order to get back up to 0. So that jump drops us below 0 for the moment, and then it comes up with the same slope that it had from L over 4 to 3L over 4. That slope like that. Wow, okay, so that is pretty wild, I think, in terms of not having to do all the math, but being able to still create a graphical representation that has meaning. Now, the question, if we go all the way back to the question, it's what is the maximum bending moment along the beam? And where is that maximum bending moment? Well, bing, 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 right? It's here, right? This is where it gets up to the maximum value. So how in the world do we calculate that? How would you calculate that without doing all the fancy math, without having to do all these integrals? Well, this is a line, and this is a line. I know the slope of this line. I actually know the slope of this line too. I know I go from from 0 to L over 4 for this slope, and I know I go from L over 4 to 3 over 4, 3L over 4 with this slope. So what does that mean? That means that if I know, or I already know this value here, right? And I know that this is L over 2 from L over 4 to 3L over 4, and I know what the slope is, it's minus R. I can take this value I've calculated and then I can add it to the L over 2 times this slope here. And remember, that's minus RR. So guess what? M max is equal to this value plus minus RR. So you see a minus RR times L over 2. And that's the value. Okay, and that's where the maximum slope is. So in this case, in other examples we talked about, taking the derivative and setting it equal to 0. That was appropriate when we had, this upside down parabola. Here, we don't have a second order system, and what we see is that we have kind of these discontinuities in slope, and actually an actual discontinuity here in the moment at 3L over 4. And so by graphing things out, we can look at the system and determine where the maximum bending moment is. Again, it's very important to be able to calculate or kind of visualize and create these graphs based on what's happening with the differential integral relationships. I hope you found this example useful. I am sorry I'm not going to run the collab this time, okay, to do the final calculations. You can do that on your own, but I hope that that this information is helpful. Thank you.